This is the final episode in rotation. So rotation has been a tough one. And this is difficult, but not nearly as difficult as some of the stuff we've already done. As always, if you enjoy this content, please give us a like and subscribe. So before we can talk about rotational kinetic energy, we just have to talk about objects that are rolling along, okay? And in this case, we're talking about rolling without slipping. So this would be like a car tire driving down the road and it's just moving along. The brakes are not locked up. If we look at the velocity of the center of mass relative to the ground, and we say that's v-com, okay, whatever that velocity is, if we then look at the velocity of these points relative to the center of mass, so now let's say this is our origin, that's our point Q, then this point up here would be traveling at v-com relative to this point right here. So even though the whole tire is moving this way, relative to this point that's moving, this point is moving at v-com compared to it. And this point down here would be moving at v-com in the opposite direction. But what if we chose that instead of relative to the center of mass, we chose relative to the ground? Well, relative to the ground, this would be v-com. So this point that we know over here is v-com is also going at v-com. So that means this point at the top relative to the ground would be going to v-com. Now on the bottom, we know that this velocity relative to the center is going this way at v-com, but the whole entire tire is moving this way at v-com, so that point is actually not moving relative to the ground. And that should make sense because that's why it's not slipping. The bottom of a tire while you're driving down the road is not moving relative to the ground. So we need to talk about two different types of motion. We have rotation and we have translation. And rotation is easy because it's what it sounds like. If we have a quarter and we rotate it, it means we're just spinning it about an axis. But when we talk about translation, that's the motion of all of the particles in a plane. So this would be translation. All the particles are moving together. Now, when something's rolling, it is both translating and rotating. So you can have both types of motion. And why is this important? It's important because we know that this object, as it moves along, has kinetic energy. Well, we haven't been using these words before, but really, all the time that we've been using 1/2 mv squared, we have been doing translational kinetic energy. But there's a second type of energy, kinetic energy, which is rotational kinetic energy. So that's it rotating. So that would be Ke equals 1/2. What's the idea of mass when we deal with rotation? That's the moment of inertia, or the rotational inertia. And what do you think this would be? Well, this is the velocity of rotation, so this is going to be omega squared. So that is Ke rotational. So we know that an object can have rotational kinetic energy by just simply rotating. And we also know that it can have translational kinetic energy by translating. But when it's doing both at the same time, we can have three different scenarios. The first one is that it's rotating very slowly, but translating very quickly. So it's hard for me to do this, but just imagine I'm slowly rotating, but I'm quickly moving. So that's a slow rotation, but a fast translation. We can have the opposite situation where it's rotating very quickly, but translating very slowly. In that case, we wouldn't have a lot of translational kinetic energy, but we would have more rotational. But what happens when the tangential speed of the rim, v tangential, is equal to v com. So when we're saying that a point on the rim, anywhere on this rim, that v tangential relative to the center of mass is the same as the velocity of the center of mass, that's when we get rolling without slipping. So that's that nice even motion that you can picture of a tire rolling across the ground. Okay, let's say we have a solid disk and it's rolling without slipping, so it's cruising along here, and we're going to use the center of mass as our origin. Remember, we get to choose our origin, so that's going to be what we're going to call our point Q, or our origin. And the question that we're going to try to answer is, what's the total kinetic energy that it has as it's rolling along without slipping? Well, if we think about it, it's rotating and it's translating. So we have two types of energy. We have Ke trans plus the rotational kinetic energy, Ke rot. So we know that Ke trans is 1/2 mv squared. And we know that Ke rot is 1/2 I omega squared. So for omega, we can say that V equals rho omega from rotational kinematics, and we can rearrange that to say omega is equal to V over R. Or if we square everything, we can say omega squared equals V squared over R squared. So we can sub in V squared over R squared for omega squared. So that will give us Ke total is equal to 1/2 mv squared plus 1/2, it's a solid disk, so that's 1/2 mr squared. And then we substitute in our v squared over r squared, and our r squareds cancel, and we have 1/4 mv squared plus 1/2 mv squared. So our Ke total is 3/4 mv squared. That's the total energy due to the translation and the rotation. But we did not have to do it that way. We could have done this and chosen a different origin. And I think this is very instructive to be able to do this problem both ways. What if we chose our origin to be the point of contact between the disk and the ground? Well, in this case, we can picture this disk rotating around that point as if it's doing that. So at a moment in time, it's rotating around point Q. So if that's the case, then we can do the same thing that we've done before, which is Ke tot equals Ke rot. But that's it. This time there's no translational kinetic energy because it's only rotating. All of the points are spinning around. They're not moving in the same direction. But that seems like it's an easier problem because all we have to do is 1/2 I omega squared. But we have a new problem because I is different. It's not rotating about its center. It's not 1/2 mr squared. We have to use the parallel axis theorem. So we have to do I parallel equals I com plus md squared. So we know that spinning about its center of mass is 1/2 mr squared. And we know that md, d in this case, is going to be our parallel axis, which is also r. So we add 1/2 mr squared and mr squared, so we get a new moment of inertia of 3/2 mr squared. So we can sub this in for our I. So that becomes 1/2 3/2 mr squared. And from before, we can use our rotational kinematics that we just did in the last step of v squared over r squared. Again, our r squareds cancel out. We end up with 1/4 on the bottom and 3 on top. So our Ke total is 3/4 mv squared, showing us that we could do this problem either way. This is a fairly common physics question to get asked. Let's say we have three different objects, three different rolling objects. They're all rolling at the same speed. So we have a solid sphere, a solid disk, and a hoop. And they're all rolling, but they're not slipping. So you can picture them rolling up the hill. Now, when we did this back in the conservation of energy problems, we would say that we have Ke turning into PEG. But it's not as simple because these are rolling. They are rotating. So they have Ke rot and they have Ke trans. So this Ke rot and Ke trans are going to be what turns into PEG. So which one is going to roll up the highest? Well, let's just sort of look at a conservation of energy equation. So we would say all of the energy we start with equals all of the energy that we end with. So I'm actually going to do this backwards. I'm going to put the PEG on this side. So this is actually the final, and that's going to be the initial. So the PEG comes from the Ke rot and the Ke trans. Now, you'll notice that if we put these equations in here, 1/2 mv squared, 1/2 I omega squared, I has mass in it, and mgh, there's mass in all three of these. So the mass will cancel out, and mass doesn't matter. So mass doesn't affect the height. Okay, well then what does? Well, what is going to be different about these three? Well, it's going to be the value of I. So really, the solid sphere, 2/5 mr squared, and the solid disk, 1/2 mr squared, and the hoop, mr squared, which one has the greatest inertia, moment of inertia? That would be mr squared. So the hoop is going to go the highest, then the solid disk, then the solid sphere. So how can we actually calculate the height? Now, I could do this for you for all three, but once you know how to do one, then you can do all of the other ones. It's the same process. So we're just going to do this for the hoop. So for the hoop, we have our energy at the end. I'm doing this backwards. Ke rot and Ke tot. So where does the PEG come from? It comes from the two types of energy, the two types of kinetic energy. So we have mgh equals 1/2 mv squared plus 1/2 I omega squared. And as you saw last time, we did a side step of V equals omega. So omega equals V over R. So omega squared equals V squared over R squared. And we can rewrite this as mgh equals 1/2 mv squared plus, what's I for a thin hoop? If you remember, it's mr squared. And we can sub in V squared over R squared. And the R squareds will cancel. The m's will cancel. And we have 1/2 V squared plus 1/2 V squared. So that's GH is equal to V squared. Or we can say H is equal to V squared over G. Now, had we done that for a different object, like a solid sphere, all we would do differently is put in the different value for I. This is basically the same problem, but in reverse. And this time, to make it a little different, we will use a solid sphere instead of a hoop. And what we're going to do here is we're going to take this solid sphere, we're going to let it roll down. It's not slipping, so it's going to roll down, get to the bottom, and it's going to roll along at what velocity? Well, we're given the height that it starts at. So we begin with PEG, and then that PEG is going to turn into Ke rot and Ke trans. So we have mgh is equal to 1/2 I omega squared plus 1/2 mv squared. And then for I, if you remember, I for a solid sphere is 2/5. So that's mgh equals 1/2 2/5 mr squared. And then we know from before, I'm not going to redo this step because we've done it twice now. That's just v squared over r squared. Plus, and by the way, I should mention this, that's only when it's rolling without slipping. Plus 1/2 mv squared, our r squareds cancel, our 2's cancel, our m's cancel, and we're going to add 1/5 and 1/2. And when you do that, you get gh equals 7/10 v squared, or we can rewrite that as v equals 10/7 gh, and that's the velocity of the center of mass. So here's another question that you might get asked. What if we had released the object and it didn't roll? It just slid without friction and did not rotate at all. Would it be going faster, slower, or the same speed? Well, think about this. When this gets to the bottom, not all of the energy turned into Ke trans. Some of that energy turned into Ke rot. So if we let it slide down with no friction, all of that would turn into Ke trans, so it would be going faster. This is a pretty cool problem. We have a rod, its length L, and that's the center of mass. And then we have a hole drilled through the rod with a fixed axle. So this entire thing can rotate like that. So you can picture it, it's going to swing down and it's going to reach its maximum angular velocity when it gets to the bottom. So the question is to find that angular velocity maximum, and the way that we can do that is with energy. So we can say the sum of the energy initial equals the sum of the energy final. So what type of energy do we start with? Well, it's not moving at first, so it has PEG. And when we look at this PEG, what has PEG? Well, it's the height of the center of mass above the axle to where that's going to spin down here. Now, this is halfway between the half, so that would be L over 4. So the center of mass will swing down L over 2. So what is it going to turn into? It's going to only be rotating. It's not going to be translating. So that's going to be all Ke rot. So we have mgh, but what's h? Well, h is the change in the distance of the center of mass, so that's L over 2, is equal to 1/2 I omega squared. But here's the problem. What's the moment of inertia? Well, it's a rod spinning about this quarter length, so we have to use the parallel axis theorem. So we have to do I parallel equals I com plus md squared. So that's going to be I parallel is equal to the moment of inertia of a rod about its center of mass is 1/12 ml squared plus md squared, and that d is going to be the distance between those parallel axes, which is going to be L over 4 squared. So that becomes I parallel equals 1/12 ml squared plus 1/16 ml squared. And if we do the fractions there and find a common denominator, that comes out to 7/48 ml squared. So now we can put in our mgl over 2 and sub in for our I, which we just found, which is 7/48 ml squared. And we have a half on both sides, and we have one of the L's will cancel with that L, and our masses will cancel, and we're left with, whoops, I forgot that omega squared there. And then when we solve for omega, that's going to be equal to the square root of 48g over L. So that's how fast it's going to be moving at the bottom. But another common question is, how fast is the velocity of the end moving? So what's the speed of this point when it gets down there? Well, we can do that with v equals rho omega. So we can say v equals rho omega and just say that the velocity of the end is going to be equal to 3/4 L, because when we look at this, we have 3/4 of L will be, that's a half L and a quarter, will be the end of this down here, times omega, which we already figured out, is 48g over L. What if we wanted to know the velocity of the center of mass at the bottom? Well, that's going to be, again, v equals rho omega, and we have v equals, in this case, it's only going to be 1/4 L, so that's 1/4 L times 48g over L. And if we look at this, this is going to be going exactly 3 times as fast. So we did this problem in the last episode when we did conservation of angular momentum. And what we had was a disk that was rotating at 10 radians per second, and we dropped another disk on top of it. Now, this is an inelastic collision, which means we're going to lose energy to heat. Now, we're not talking about the energy during the collision. We're talking about the speeding up of the, or the slowing down of the disk, the speeding up of this disk once they come together. Now, I'm not going to redo this whole problem for the final angular velocity. You can go back to the last episode to see that problem. But the way it worked was we did it with sum of the angular momentum initial equals sum of the angular momentum final, and we found that the omega final, and this is of the system, this is of the two disks once they're moving at the same angular velocity, that came out to 9.5 radians per second. So how do we figure out how much heat was lost? Well, we're going to do that with conservation of energy. So that's going to be sum of the energy initial equals the sum of the energy final. Well, what type of energy do we have to start with? Well, this is not translating or rotating, so it has no kinetic energy. And this is rotating, so it has kinetic energy. So we're going to start with Ke rot of the big disk, which we were calling disk 2 initial, is equal to, and then we have Ke rot of the second disk after, and that's going to be slower than what it was going before. It's only going 9.5. And then we have Ke rot of the smaller disk, so we'll call that disk 1 final, plus the heat produced. So what do we have here? Well, we have 1/2 I2 omega squared equals, and that's omega initial, equals 1/2 I2 omega final squared plus 1/2 I1 omega final squared, and these two are the same. So we could factor that out, but I didn't do it. Would have saved a little bit. And then we put our numbers in. So this is a solid disk, that's 1/2 mr squared, 1/2 mr squared, and 1/2 mr squared. So that becomes 1/2 times 1/2 times the mass, mr squared, that's 6, times the r, which is 0.5 squared, times the initial angular velocity, which was 10. Then we have the disk after, so that's a 1/2, 6.5 again. But the difference on this is that it's moving at 9.5 radians per second. Then we have the smaller disk, so 1/2 mr squared is 1/2, 1/2. M was 2 at a radius of 0.2 times 9.5 squared plus Q. And when you do all the math on that, so quite a few steps there, but when you do that, you get 1.9 joules of energy left over on the other side. That's what's missing, so that's our heat lost. Here's another question, and we're only going to do the last part of this question because we did this in the last episode as a conservation of angular momentum problem. So what we had was a ball that comes in and hits a rod. This is in space. The ball bounces back and the rod starts to rotate and translate. So that should tell you two things. It's rotating and translating. In other words, it has rotational KE and translational KE. So the question is, what's the heat lost? And before you can do that, you have to solve for this omega and you have to solve for this VCOM. And how do you do that? Well, you do that with linear momentum conservation. Sum of linear momentum initial equals the sum of the linear momentum final. And you can do conservation of angular momentum to get omega. So you get this and you get this. And once you have these, then you can solve for the heat lost. So what does that look like? Well, we're not going to put all the numbers in, but I'll just show you how you do it. So you have all of the energy you start with equals all of the energy that you end with. And what do we start with? Well, we start with KE initial of mass 2. Okay, so the ball comes in, nothing else is moving. This is the only thing that's moving. So this is the only thing that has kinetic energy. So that initial kinetic energy is going to be M2, and that's translational. Okay, so that right there would be trans. So all we'd have to do is 1/2 M2V squared. Then that's equal to the KE final, which is going to be a whole bunch of things. That's going to be KE final trans of the ball. That's M2. So this ball has kinetic energy. Now, it doesn't matter that it's moving in that direction because this is squared. You can also think of it as a scalar. So as long as it has energy, it doesn't matter the direction it's moving. So that's positive. Plus, what else do we have? Well, we have KE trans of the rod. So that would be mass 1. So the rod is rotating, and because we have the velocity of the center of mass, we know what that is. That's 1/2 M1 VCOM squared, plus KE rod, it's rotating, and that would also be for mass 1, and that would be 1/2 I omega squared, and I in that case would be 1/12 ml squared because it's a rod rotating about its center of mass. And then finally the heat lost. So this initial kinetic energy, we could just make up a number. Let's say this is 10. Then the sum of these three would be less than that initial kinetic energy of the ball. So let's say these added up to 8, and we started with 10. Then, whoops, I should have said Q. I think I said Q, but I didn't write a Q. That heat lost would be 2 joules left over, whatever the leftovers are.